Good morning, everyone. My name is Zheng Chen. Again, I'm an assistant professor in NanoEngineering department, starting my 4th year. So actually, I don't have so many awards to show. yeah. yeah. And to be frank, I didn't get 200K or 100K from research corporation, but really, I get very much benefited from research cooperation. Is really stimulated and helped me to be very persistent in solving an issue that no one cares at the very beginning. Okay, yeah. So so I'm trying to talk about some sustainability issues. Okay, so again, I work in very different field, which is more like engineering. I'm trying to solve practical issues, short-term and long-term issues as an engineer. So this is basically a lot of these projects are funded by companies. Actually, they see we have a very short-term benefit, so they are very interested. But the majority of my work in my lab is not very interested to a lot of people, which is doing battery recycling. Okay, so I'm not going to talk anything about these practical issues, but the reason I'm talking about battery recycling, okay, is really about a huge issue looking for next 20 or 30 years. Okay, so this is what I'm trying to show here is the basic structure of batteries. So no matter what kind of batteries, your cell phone, laptop, electric vehicles, they're all made by very similar structure, cathode, anode, separated electrolytes. So what I'm trying to highlight is the material that is used in batteries. Okay, these are many different types of materials. Okay, some of them, okay, I want to highlight cobalt, nickel, cobalt, nickel. So they are dominant material used in batteries to make your cell phone to run for more than one day. Otherwise, if you use some other material, you have to charge 5 times a day. Okay, so more bigger issue, actually a big issue is talking about electrification of transportation, grid storage, and integration of renewable energy to your house, to utilities, to the grid. Okay, so I'm trying to ask you a simple question. Anyone knows, okay, how many cars were sold last year in the world? Anyone knows? Number? 5 million? 10 million? 20 million? Almost 100 million, yes. Okay? A lot of countries, United States, European countries, they are talking about replacing these cars, okay, by electrical power source, which is battery, okay? We're not talking about 100% replacement. Let's talk about 10%, 20%, 50%, right? You see the news, some countries has proposed by 2030, we're going to replace them, okay, by 30%. It's very ambitious. We're talking about 500,000, okay, 50 millions of electric vehicles a year, okay? So this will drive a huge problem in the demanding of materials. Actually, we're going to use a lot of these precious metals, okay? So cobalt is one example I want to show, okay? So the global reservoir of cobalt is only 7 million tons, okay? And 60 of them is reserved in a small country, okay? Congo, okay, in West Africa, okay? And this cobalt is mined, has been mined, okay, by children neighbor, okay? This is a few years ago. Now, other companies like Tesla, Apple, they have found these issues. They are trying to resolve the issue. So this is an old issue, old problem, okay? So I'm also trying to show in United States, okay? So this is basically also a huge number, okay, in the combustion engine cars. We're trying to replace them, okay? So we're talking about recycling. Okay, actually, lead-acid battery has been very well recycled. Okay, but talking about lithium-ion battery is a different story. Okay, so right now we have approaching at least 1 million electric vehicles in US sales. However, less than 5% of them have been recycled. Okay, and then so typically around 2 to 3%. Okay, so we're talking about future years. Okay, so if we don't care about that today, okay, we will have to leave it for our next generation. Okay, what are they going to do? Okay. However, recycling of lithium-ion battery is so difficult. They're not going to make any profit. No one is going to do it. Okay. So no one is going to do it. It's very complicated in terms of their structure, composition, and the materials. Cathode, anodes, electrolyte, they're all different. Some of them are polymers. Some of them are liquid. Some of them are toxic. Okay. Some of them has made by high temperature process approaching 1,000 Celsius degree and fairing for about 20 hours. Okay. How can you recycle them for such a different material? I mean, classifier of materials. Actually, at the very beginning, when people first make a cell phone using lithium batteries, they are thinking about recycling. However, for today, I want to emphasize again, compared with metals, tires, papers, very small ratio of batteries have been recycled. Okay, so what I'm trying to do, I have been trying to do at the very beginning when I started my career in UCSD. I asked my first postdoc to try to think about battery recycling. I asked my first PhD student to think about it. No one is interested, okay? I have to persuade them, okay? You have to do it. Otherwise, I'm not going to sign your thesis, okay? Yeah, I cannot renew a contract, you don't do it. Okay, I have no funding, okay? So I just use my startup, okay? So basically our idea is to take a battery and think about how they degrade, understanding degradation history, and how we can basically leverage reversal chemistry by understanding fundamental properties that are happening on the surface, in the bulk, and on the interface, okay? In the end, we generate a very mild process, which you put a very little bit of energy, very little amount of chemicals to recycle them, to make them from older material to new materials that you can readily use them to make new batteries, okay? So we claim both materials and we claim energy, okay? So because of time limit, I'm not going to show all the details, all the characterization, all the transmission, electron microscope, and the spectroscopy data. But what I'm trying to show is the entire process. Basically, we combine two engineering processes. One is a solution process. One is a very short and linear process. In the end, we can make this defective structure into this well-defined structure, which is what we need for making new batteries. Okay, so I'm showing some like SEM, scan electron microscopic images show how we make it work. And then in terms of morphology, we make them back to the original morphology because there's very little change. Particle size distribution from new battery to old batteries, and then from to regenerated battery material composition, we get them back. Okay, so this is unfortunate, as I said. Okay, I eat my word. I do have some spectral data. Okay, so this is Raman spectroscopy showing that from old batteries you have these small peaks, which is because of degradation, and after our process, we make them back into the original spectrum, which has no side peaks, which means we make them to be very good in terms of their phase composition, okay? So these are electrochemical data with which we test the batteries in our machine, and we see how much is the power, how much is cycling stability. So we're showing here we can operate in a very broad range of conditions in terms of time and the temperature to very effectively recycle lithium battery materials, okay? So this is just one example. So we're talking about in terms of the current and future battery materials. So people are proposing many different material, okay? So some of them are very expensive, some of them are very cheap, okay? So let's see, we're talking about this material. It's going to be used in batteries sooner or later, okay? It's $1,000 per kilogram, okay? So we can use some of them are slightly cheaper, okay? But in the end, they're not even comparable to natural material, available materials, for example, graphite, okay? And then we're trying to think about how can we further reduce the price, reduce the demands on continuously mining natural resources. So this is what I'm still focusing doing in my lab. So no matter what kind of material you're using, think about, okay, if one day we want to use them by a huge quantity, okay, no matter how much is reserved in the world, like water, right? If the global population increases by many folders, okay, we're going to run out of water, run out of food, right? Run out of land. Of course, run out of house, right? Housing price increase crazily, okay, everywhere in the country, okay. So this same idea. So in my lab, I'm trying to push the boundary of understanding the properties of battery materials and proposing new solutions to solve them, okay? So as I said, the reason we're doing this is number one is the passion. The another reason I'm really persistent in doing this is because I'm going to come back to what I'm actually get benefited from participating in research cooperation conferences. So as I said, I didn't get the cultural award, but okay, a very important reason I want to appreciate research cooperation is that they really bring us, okay, to the location that we have very strong, very useful brainstorm. For example, I talked with this year's Nobel Prize, or previous year's Nobel Prize winner, Dr. Sterling Whittingham, who actually, for today, if I'm sending him 100 emails, he probably not have time to reply, okay? But research cooperation really identify the person, the leading person, the young scientist, to sit together on the same table, okay, to discuss really the important questions that we are trying to do or we have to face for the next few years, next 10 or 20 years. So by talking with Stan Whittingham, I really become very clear and more persistent in saying This is also by that time, 2-3 years ago, no one is funding us, and I'm still very personally using my huge portion of startup funding to get that, okay, to make it, to study that. So in the end, actually starting from the support from a research cooperation with Natan, we started get approached by directly. I'm not approaching DOE, but US DOE come to my lab to say, oh, what you are doing is really interesting, is really promising. So they formed this nationwide battery recycling consortium, which brings us to be one of the core members. And the National Science Foundation also provides us considerable amount of funding to continue explore new chemistry and new process. And a lot of private companies later on realize, oh, this is really the problem we have to solve. So we have been continuously approached by a lot of private companies, and we are doing many different processes and try to not only understanding fundamental issues and trying to bring the process in developing our lab into the commercialization level of applications. So with that, I would like to thank again to Research Corporation, especially Richard, who have been spending so much time, and sometimes we have been very slow in responding to emails. He was very always so kind to accommodate our needs and help us to get to new opportunities. So I also would like to thank for your attention. I will be very happy to answer any questions if you have. Yes.
So when you regenerate the batteries after 200 cycles, and you show that they now don't have the decomposition that develops, do they now last the same length of time as the original batteries?
It's a good question. Okay, the question is that you recycle the battery, when you get new material from recycled process, you then show the same property. Okay, so the answer for my process is yes. Okay, so sometimes, to be frank, we get a slightly better performance. The reason is that in my lab, okay, in the lab we're running a small scale, right? Industry is running in terms of thousands or tens of thousands, tens of scales. So they have some kind of so-called impurities, or in our field we call it cation mixing, which caused some slightly lower quality of material. So, but I imagine if we bring up or scale up from a few grams or a few kilograms scale in my lab, going to the thousand and tens of thousands scale, we will face the similar issue. But in terms of demonstration of the property, we use a lot of characterizations, very intensive testing methods to show that we have no problem to get a material property back to the same level of pristine material. Yeah, not everyone, for a majority of the material used in batteries. Yeah. Yes.
Is recycling a factor in battery design?
That's actually what we are pushing very, very hard. So it's an old question. So industry, so for making batteries, so we're not talking about investment in millions, we're talking about billions of investment. That's why the current manufacturers, they are so resistant in changing their production design line, okay? So what I'm trying to do in the next is basically really trying to change their mind, okay? So batteries have been designed 20 years ago from Panasonic, from Sony, okay? So they designed the batteries, and everyone just copying their original design principle, like Tesla. They are still using the same cylindrical cells, okay, that has been developed 20 years ago, okay? The reason why they don't want to change is because change them, you need to have a lot of capital investment, okay? The workers has been retrained, okay? The engineer has been retrained. So, but the problem is that this battery has no clue about how to recycle them. For today, we realize this is going to be a huge issue. The global demand for batteries is going to be 1,000 or even 1 million higher than original thought. So we're trying to think, can we design batteries, okay, using the best chemistry, the best material, the most abundant material, okay, and using the easiest structure to make them so that once you want to recycle, you can easily recycle them, okay? Like plastics, people are designing so many plastics, they went to the ocean in the end, okay? There's no solution for them for now, okay? So what I'm trying to do is try to design better, very beginning, okay? Try to persuade not only, colleagues, but also industry partners. We hope they can implement such a design principle into their manufacturing process, okay? But this really, needs a lot of effort. They are very resistant in doing so. So we are trying to persuade them to think about it. Okay. Yes?
Could you speak to the ratio of the energy that's used in the recycling or conversion process
Mm-hmm.
relative to the length or the energy that can be produced through the battery itself? What kind of advantage is proportional to these cycle efforts?
Okay, so this is a tough question because it depends on how long your battery can last, right?
Yeah.
So definitely we need better materials. For today, your cell phone, you want to change your battery, probably now you cannot change it because iPhone changed the design. You cannot open your cell anymore. But I mean, let's say 2 or 3 years. Okay, for cell phone, electric vehicles, we're talking about 10 years. For grid energy storage, for utility storage, we're talking about 20, 30 years. So your battery can last longer. Definitely your energy input, your energy generation and the storage will give you much more benefit compared with recycling. So what I would say in another way is to compare with primary mining, primary manufacturing process by do not do recycling or do recycling. What is the difference? Okay, so in the lab we also do a lot of life cycle analysis. Okay, so in terms of energy saving, we save 70% of energy by our analysis, but this is not actually the main concern. The main concern for us is really the pollution. Okay, so mining material from natural ores and using very strong acids and high temperature process to get cobalt, for example. In natural ores, the abundance of cobalt is 0.2% only. Okay, so in your cell phone is 10%. In the older battery is 10%. That's the one thing you want to ship cobalt from Congo, okay, to Asia and then to US. Okay, think about the entire process costs you so much energy. Okay, so running energy, you have to burn coals or do whatever things to generate CO2 and SO2. So this is really the big issue. Okay, so considering recycling will not only save cost, save energy, but also significantly reduce the pollution which is associated with your manufacturing process. Yeah.
Thank you so much again.
Okay, thank you very much.